All right, hello everyone, and welcome back to Calculus 2. So today we're learning about the ratio test and about absolute and conditional convergence. So first of all, what is absolute convergence? So if you give me a series, and maybe that series has some positive terms or some negative terms, maybe a mix of both, what I could do is I could think about just adding up the positive version of every term. So taking the absolute value of every single term. And this is what leads us to our definition of absolute convergence. So given any old series where the sum or where the terms could be positive, negative, mixed, yada yada, if we know that the sum of the absolute values of all the terms is convergent, then we call the original series absolutely convergent. So again, if we call the original series absolutely convergent if when we take the absolute value of every single term and add that up, that series is convergent. So for example, this series has a mix of positive and negative terms. If we start looking at it, we have positive term, positive term, negative term, yada yada. It's alternating between positive and negative. If I then, instead of thinking about the original series, if I think about this new series where I take the absolute value of every single term, it's really just the same thing as taking the sum of 1 over n squared, right? So I change all these negatives to positives, and I get the series 1 plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, so forth. And if we think about this new series, we know that converges. That's just a p series where p is equal to 2, right? And so because this related series converges, we call the original series absolutely convergent. Notice, right, so far all I've said is this converges. I don't know if the original series converges or not. But it turns out there's actually a theorem that says that whenever the absolute value version of the series converges, then the original series converges. So if I kind of think through our sort of set of options, if I know this converges, what we're saying is then the original series has to converge. And what we don't know about is in the setting where the sum of the absolute value diverges, then maybe we could have that the sum converges, or maybe we could have that the original sum diverges. Oops, sorry. All right, so we kind of have 3 different settings now. Before we were thinking about just converging or just diverging, and now we kind of have some subsets of converging and diverging. All right. We've already said that this setting is what we call absolutely convergent. It's where both the absolute value of the series and the original series are both going to converge. This series where the absolute value diverges and the regular series converges, we're about to look at that, and that has its own name. This is called conditionally convergent. All right, so these are the 2 settings where our original series converges, right? We've got these 2 settings. And so basically we've taken convergence and we've divided it into 2 categories, conditionally convergent versus absolutely convergent. And of course we have final version of things where both the absolute value diverges and the original series diverges. And this is just where we would call the original series divergent. So it's kind of Venn diagramming here. Okay, so again, like I said, conditional convergence, that is when our original series converges, but the sum of the absolute values doesn't converge. So this converges, but this does not. So that is what conditional convergence looks like. Turns out we've talked about some examples of conditional convergence, likely in your classes before. It's already been sort of mentioned. So here's an example that you may have seen before. It's called the alternating harmonic series. So it turns out if you essentially take the harmonic series, so the sum of 1 over n, but you change the sign each time. So you do 1 minus 1/2 plus 1/3 minus 1/4 instead of just doing plus each time. Turns out this series converges. But we know the absolute value of that series, which is just the sum of the 1 over n's, we know that diverges since it's a p series with p equal to 1. Right? So because the original series converges, but the absolute value version diverges, we say that this is conditionally convergent. So that's our two big new pieces of vocab today, is conditional convergence versus absolute convergence. And if you think about it, the tools that we have had so far may or may not help us, because most of the series tests that we've used have required all the terms to be positive already. And so if I wanted to know if this series converged, I actually don't really have many tools right now to apply to figuring out if the series with non-positive terms, if that series converges. And so we're also going to build up a new test today called the ratio test. So again, we're just looking for a test that can help us when not all the terms are necessarily positive. And so we'll have this test, and then the next video will be about the alternating series test, which will also help us in these settings. Okay, so the ratio test, right? We're looking at some sort of sum of ANs. And our ratio test tells us to consider the limit of the next term divided by the previous term and take the absolute value. Okay, and let's say that that limit equals L. So the ratio test says depending on what L equals, or what the value of L is, we're gonna know different things about our original series. So if the limit of the absolute value of the next term divided by the previous term is less than 1, then we actually get to conclude that our series is going to be absolutely convergent, unless it's going to converge, of course. If the limit is greater than 1 or infinite, then our series we know is going to be divergent, our original series. And if the ratio, if this L equals 1, then we actually don't know what happens. It's inconclusive. So we don't know if the series is going to converge or diverge. We would have to go forth and use different series tests in order to be sure about that particular series. Okay, so let's see an example of this in practice. So if we look at the series, the sum from n equals 1 to infinity of -1 to the n cubed over 3 to the n, let's see what the ratio test has to say about that. All right, so ratio test, again, asked us to do limit as n goes to infinity of an plus 1 over an in absolute value. All right, so in this case, that's talking about doing the limit as n goes to infinity of, let's see, the next term, so -1, the n plus 1 cubed, divided by 3 to the n plus 1, divided by the an term, so -1 to the n cubed, 3 to the n. Of course, I know when I multiply or when I divide fractions, I need to flip and multiply. Right? So this is the same thing as the limit as n goes to infinity. Absolute value, -1 to the n plus 1, n plus 1 cubed, over 3 to the n plus 1, times 3 to the n over -1 to the n cubed. And again, all this is still in absolute values. Okay. We're going to continue simplifying that down. So that's the same thing as, let's see, limit as n goes to infinity. Let's see, most of the -1s cancel. I'm left with just one copy of -1 in the numerator. Most of the copies of 3 cancel, other than one copy that's in the denominator. And then I have n plus 1 cubed over n cubed. Okay. All right. And as I'm looking at this, everything here is going to be positive except for that -1. So I don't even need that, right? I can drop that and drop the absolute values at the same time, right? That's the only thing the absolute value is doing for me, is canceling out that -1. So really, I'm looking at the limit as n goes to infinity of n plus 1 cubed over 3n cubed. In fact, let's go ahead and just FOIL that out, right? So looking at n cubed plus 3n squared plus 3n plus 1. Okay. Then we have 2 tools right now. If we want to go through and do the careful calculus version, we're going to do L'Hopital's rule a few times because we have an infinity over an infinity limit. Or if we think back to our pre-calculus knowledge, we know that we can really just think about our highest order terms, right? So this is the same thing as the limit as n goes to infinity, n cubed over 3n cubed. N cubes cancel. So this is the limit as n goes to infinity of 1/3. That's just a constant, so we get 1/3. Okay, so we know for this version of the ratio test, we have found that our L is 1/3. If we think back to that, our ratio test said that if our ratio is less than 1, then our series is absolutely convergent and therefore convergent. So since our L is less than 1, thus we get to say our series that we were given converges absolutely. That is our final answer based on the ratio test. Let's do another example. So we're looking at n squared over n factorial. Ooh, interesting. We haven't had many tests that seem to be useful for factorials yet. Okay, let's test this using the ratio test. So we want to look at the limit as n goes to infinity. Let's see. Okay, so we do the n plus 1 term. So n plus 1 squared over n plus 1 factorial divided by the n term, so n squared over n factorial. That's the same thing as, let's see, flip and multiply. So n plus 1 squared times n factorial over n plus 1 factorial times n squared. I'm gonna notice 2 things right now. So first, the n factorial cancels with the n plus 1 factorial and just leaves me with a factor of n plus 1 in the denominator. And the other thing that I'm noticing is that the absolute values really don't matter here, right? I don't have anything that's negative inside of there. So I'm gonna take care of both of those in the next step. So I'm really just looking at the limit as n goes to infinity of n plus 1 squared over n plus 1 times n squared. All right. Factor of n plus 1 cancels in the numerator and in the denominator. So I'm left with just n plus 1 over n squared. And again, we can do L'Hopital because we've got infinity over infinity, or we can think through our pre-calc knowledge. I've got a lower power in the numerator. So the limit as n goes to infinity, it's going to end up equaling 0. So our L in this case is 0. Again, think back to what the ratio test says. If L is less than 1, we get to conclude that our series is absolutely convergent. By the ratio test. All right, and so we are on to our last test. Go ahead and try to decide if this converges absolutely or conditionally. So yeah, go ahead and pause here and think through that. So turns out if you do the ratio test, you're going to see that this series actually diverges by both the absolute value of the series and the regular series both diverge. So there you have it.